Hello everyone. In this video we are going to study one of the most important topic in advanced machine learning, that is model selection. First we will see why does model selection really matter. First, every algorithm has its own bias. Some are better with numbers, others with images, and so on. Second, the data itself plays a big role. The shape, size, and quality of your data can make one model performer far better than another. Third, there is no one size fits all model that what works great for one task might fail completely in another. And finally, a good model choice can literally boost your accuracy up to 20%. Now that we know why model selection is important, let's look at how we actually do it. First, we use cross validation. This means testing the model on different chunks of data to make sure it works well overall. Then we tune the model settings with techniques like grid search or Bayesian optimization to get the best results. Finally, we use regularization to avoid overfitting, basically telling the model not to get too clear and memorize the data. All of these steps helps us choose a model that performs well not just in training but also in real world situations. Let's dive deeper into cross validation. First, we split the data into k parts and rotate through them. This is called k-fold cross validation. To make things fair, we often use satisfied folds, which make sure that each group has the same class proportions. For extra precision, we can do leave, leave one out where we test one point at a time, but it's very slow. The main advantages of all this is what we reduce variance and get a much more stable estimate of how well our model will do in the real world. Now let's talk about hyperparameter optimization, the art of fine-tuning models for top performance. The simplest method is grid search, which checks all combinations, but it's slow. A better approach can be random search, which saves time by sampling randomly. And if you want something smarter, go for Bayesian optimization. It learns from previous atoms and predicts better values. Tools like hyperparameter make this easy in Python. All of this helps you squeeze the best out of your models without wasting time. Let's talk about regularization, the guardrail that keeps your model from overfitting. First is L1 regularization or lasso. It not only shrinks weight but can even eliminate unimportant features, making the model sparse. Then comes L2 regularization and called ridge, which shrinks weights smoothly and prevents them from becoming too large. If you want the best of both worlds, use elastic neck. It makes L1 and L2 for a balanced effect. And don't forget alpha tuning. It decides how strong your regularization is. As you can see in the chart, too little or too much regularization can hurt. The goal is to hit that sweet spot. Now that we have built our models, How do we pick the best one? The answer lies in the evaluation matrix, but which one you choose depends on the task. For classification, you might look at accuracy, but if your classes are imbalanced matrix like F1 score or AUC ROC are more informative. In regression, it's all about error, whether you use MAE, RMSE, or R squared. It depends on your tolerance for big errors. And don't forget the business line. Choose what really matters for your use case. Next, we will see the bias variance trade-off. Let's look at this triangle. At the top, we see the optimal balance. This is when the model generalizes well to new data. It's neither too simple nor too complex. This is the ideal situation. In the middle, we see high variance. This means the model is too complex and overfit the training data. It learns the noise instead of the actual pattern and performs poorly on unseen data. At the bottom, we have high bias. This happens when the model is too simple, it underfits the data and cannot capture the actual trend. Next, let's go over some practical considerations to keep in mind when building or choosing a machine learning model. First, computational cost. When we train a model, especially large ones, they can take a lot of time and computing power. So it's important to consider how long training and evaluation will take, especially if you are working with limited resources. Second, interpretability. Interpretability means how easily we can understand the decisions made by the model. This is especially important in fields like healthcare or finance, where understanding why a prediction was made is crucial. Third is data limitations. Every model depends on data. If the data is limited in quantity or quality, it will affect performance. So always check if your data is reliable and complete enough for your use case. Fourth, start simple. Let's a good idea to begin with simple models first, like linear regression or decision trees. They are easier to train, interpret, and debug, and sometimes they perform just as well as complex models. Let's wrap up by looking at some of the best practice for selecting a machine learning model. These are essential steps to ensure your models performs well and meets your objectives. First, understand data. Before choosing any model, you must understand your dataset. This includes understanding the features, data types, and the problem you are trying to solve, whether it's classification, regression, or something else. Next, align with goals. Model selection should align with your business or research goals. For example, do you prioritize accuracy, speed, or interpretability? Choose models that best serve your specific needs. Next, cross-validate. Always use cross-validation to evaluate models' performance. It helps ensure that your results are not due to random chance and gives a more reliable estimate of how the model will perform on unseen data. Fine-tune hyperparameters. Every model has setting known as hyperparameters. Use techniques like grid search, random search, or Bayesian optimization to fine-tune these for better performance. Finally, regularize Regularization helps to prevent overfitting, which occurs when a model learns the noise in training data. Techniques like L1 or L2 regularization make the model simpler and more generalizable. Together, this best practice will help you build models that are accurate, efficient, and robust. Thank you.